Hello and welcome to this EduSet presentations, and the topic for my discussions will be Internet Protocol Part 2. In these sections we will talk about the various components of the IP package. Now IP package is a huge package and it has many components. Let's say here I will design. If this is my IP package, it contains several modules are there. One is called the header adding module. So it has many packages. We'll define what are basic components of this package and define each one separately now. One is the header adding module. It has a processing module. This is the central component of IP package. This is called processing module. So once you understand what are different components are there, you will understand how the IP packets, how the IP really works now. So the processing module, we have a forwarding module. It basically forwards the packet from one router to the another router. So we call them short form. I am just writing FM, forwarding module. It is a processing module. The first one is I have named them as a header adding module. We have then there will be fragmentations module, because the packet is not all the routers will able to handle the 64K size of the IP datagram. So it tries to break them into several fragments, and finally these fragments have to be reassembled at the end now. So reassembly is done only by the end module, by the destinations module itself. So there will be fragmentations module which will fragment them. There might be reassembly module. Then we have similarly with each of these modules we have large number of data structures associated with it. So there is a reassembly table, there is a routing table, we have a maximum transfer unit table which is basically consulted by the fragmentations module, and so on and so forth. So these are the basic important components and important data structure. Let me just revise once again, and by understanding each of these one you will understand how the IP works. We have header adding modules, which basically purpose is to add a header. Then we have what we'll call them, it goes to the processing module, which is a central component of the IP package, which really processes your IP datagram. Then it can go to the reassembly module, it can go to the forwarding module, it can go to the fragmentations module, and finally each of these modules has associated data structure named as a reassembly table. We have a basically routing table, we have a MTU table which is consulted by the fragmentations table, and also we have certain queues, input queue and output queues. Input queues is basically used to store the datagram coming from the the information coming from the top layer, and then we have the output queue which is basically used by the IP datagram to send the packet to the upper layer. Now each one basically let's try to go now. Now let me define the algorithms and logic of each one separately now. What the header adding module does. We write a small algorithms in form of a statement, not in form of any programming language notations, simply that you understand what exactly it happens now. So to understand the complexity of these simple protocols like IP protocols now. So header adding module, HAM, I have simply named them. So the first step is what is the input. Each algorithm receives certain data and processes the data and gives certain sort of output now. So what is the input of this one? Input is that it receives data, it receives destination address. So input to this module is the data has to be there, and it has some destination address which is coming from the upper layer now. Now what it does is basically encapsulate. Basically function is encapsulate the data in the IP datagram by adding the IP header. This is basically primary responsibility of this header adding module. Now what is the first step it does? Encapsulates the data into the IP datagram. Remember that IP datagram comprises of two fields, the header fields and the data fields. So it encapsulates the data into the IP datagram. The first one is then it calculates checksum. Initially this value, checksum value is 0, and then Then finally it calculates it and encapsulates this value into this field. How it calculates the checksum value? That it takes the whole IP header as a 16-bit sections, and it adds each sections of n bits, and finally what it does is it takes sum of all the section of n bit individually, and after taking the sum, it complements it. It takes one's complement of this one, and whatever value it gets, it inserts into this one. Let me just revise once again. Checksum is important field of the IP header or IP datagram. How it does is that it divides the IP header into the several sections. Each section size is 16 bits. It add all the subsections or add all the sections of 16 bit each. After adding the sum, it takes one's complement of this one and then adds this value of checksum into the checksum field. Initially this checksum field is 0. So after adding this checksum field, it finally sends it further. So first encapsulates the data into the IP datagram, then calculates the checksum value. Initially it's set to 0, and then send the data to the corresponding queue, and then finally return. So these are the 4 steps it follows. It encapsulates the data, that is first task, calculate the checksum, that is the second task, then send the data to the corresponding queue, and finally it returns it. So this is what the header adding module does. Now, and the input to the header adding module is the data and the destination's address, which is received from the upper layer. Now let's go to the processing module. As I told earlier, the processing module is the most important component of the IP package. So we'll just talk about the processing module now. Now the processing module is first checks whether datagram is a loopback packet or not, and I will later on define what exactly is the loopback packet. There is a specified address number. If it has that address, that destination's address, then it is considered to be a loopback packet now. Then in case it is a loopback packet, it is sent to the reassembly module. Otherwise it does not do. If so, the first task of this one of a processing module is to check whether the datagram is a loopback packet or not. How it able to check this? By checking the destination address. If destination address is of certain value, then it is a loopback packet and it's sent to the reassembly module now. If the node where the datagram is being processed is a router, then it try to decrement the time to leave value. TTL is one of the field of IP datagram, which basically decides that how long this packet will be in the net, right? If the value of TTL is less than or equal to 0, then it discards this datagram packet and sends the ICMP or error message now. If the value of TTL is greater than the 0, then it basically processing module sends this datagram to the forwarding module. So these are the important tasks to be performed by the forwarding module. Checking whether the packet is a loopback packet or not. In case it is not, then it checks if the processing module, if the node is a router, it tries to decrement the TTL value and checks whether it is less than 0 or 0. If 0, then packet will be discarded or stopped there itself. If not, then it will be forwarded to the next router for processing now. Now, as I just explained, let me just write them in form of algorithmic notations now. So what I am trying to do is writing the algorithm of a processing module. Processing module, as I told earlier, it is a central component of a IP package. Any package, any datagram has to be processed. Now so what it does is the step number 1, remove one datagram from the input queue. It maintains, as I told you earlier, that the IP package contains large number of modules. Processing module is one of the modules of IP package. Besides this number of modules, it has several data structures in form of a table, the routing table, the MTU table, reassembly table, fragment table, and so on. And then we have a number of other queues like input queues and the output queues. So remove one datagram at a time. Remove one datagram. I'll just write down in form of a DG. Remove one datagram from one of the queue, one of the input queue. The step number 2. So once it takes one datagram at a time, now it checks whether the destination address of this IP datagram, if the destination's address of this IP datagram is this value 127.x.yz, something like this, or matches one of the local addresses, then send this datagram to the reassembly module. This is a part of this one. If this condition is met, then send this datagram to the reassembly module, and finally you return it. This is my first task. 2 tasks I have performed. First, I took the datagram from the input queue, which is maintained by the IP package. I examine the destination address of this packet. If it is 127 dot something, then the packet will be sent to the reassembly module and finally return. If next case, if the machine is a router where we are trying to process this datagram, if machine is a router, what it does is decrement the TTL value. First, decrement the TTL value. TTL stands for time to live, how long this packet will be in the net. This is one of the field of the IP datagram. If the TTL is less than or equal to 0, means already it has survived, I mean his time is over, then discard the datagram. It will reject the datagram. It will not able to forward it further. It will discard the datagram. Send the ICM package. We'll send the ICM package here. ICMP package it will send, and finally it will return now. In case this is not the case, means if the package has value more than 0, then the packet will be sent further to the next routers and so on. This is one thing. So this is the second module which we discussed. As I told earlier, we have input queue. There is input queue here. There is output queue here. You see another 2 important data structures are there. One is input queues are basically store the datagram coming from the data link layer or the upper layer protocols, where output queues store the datagram going into data link layer or upper layer protocols. There is a routing table is used by the forwarding module to determine the next hop address of the packet. Then we have a forwarding module which simply sends, I am not writing the algorithm, it sends the packet from one machine to another machine. There is a called MTU table. These are the important data structure. MTU table. MTU means maximum transfer unit table, which basically this is used by fragmentations module to decide whether the packet has to be fragmented or not, and the certain format has to be followed. Let me go to the fragmentations module. This is very much important module because I told that not all these frames, all the data link layer handle such a big, huge IP datagram, so they try to break them into smaller chunks, but there must be some mechanism to reassemble at the destination side. So let me just see let me start with the again fragmentations module. What this fragmentations module does is what is the input? The input is some IP packet from a routing module. There is a routing module which I have not written. It's basically based on the routing algorithms. it consults some routing table. So now what exactly it does is, so input is some packet which has to be fragmented because the size cannot be handled by all the routers. Then in this case, what should be, how it has to be fragmented, what should be basic logic of fragmentations. So here is we are writing, the first is extract the size of the datagram. This is the first logic, first part of this one, extract the size of the datagram. Two, if the size of this datagram is greater than the system can handle, greater than the MTU, maximum transfer unit at that router level of the corresponding network. If this is bigger, it means that it has to be fragmented. Then what we have to do is, if again checks, if D there is two basic fields of a fragment, the D and M. D stands for do not fragment, M means for more fragment. If D means do not fragment bit is set, if D is set, then you can then discard the datagram. You cannot forward this packet because it's too big for this router to handle this one, and also the D bit is set to 1. Discard the datagram. Again as usual, then send the what we'll call them, send the ICMP message, error message that it cannot be forwarded, cannot be processed, and again return. So this is the one part of this algorithm where we are trying to check the size of the IP fragment with this MTU, maximum transfer unit, which can be supported by this machine, by this local machine or the network. If D is set to 1, means do not fragment, you cannot handle it, simply discard it and send the error message called ICMP. Then come to the second part, else, means if this is not the case, then what we have to do means that this is true but this is false. Then in this case, calculate the maximum size. Calculate the maximum size. Next will be divide the datagram into fragments. So first I will calculate the maximum size, divide the datagram into fragments, add header to each fragments, add required options to each of these fragments, send the datagrams and then return. And finally, so this is what basically you have. So these are the basically you can do. Else send the datagram, means that if system can handle such this one, so finally will be else send the datagram. Let me explain once again, so that this is a complex algorithms. The purpose of this one is what the fragmentations module does. The purpose of the fragmentations module is to fragment the datagram if the machine cannot handle such a huge datagram, and it does only when the D is not set. In case D is set and the size of this packet is greater than the MTU, then simply it will discard, send the error message, send the ICMP message, and then finally it will return it. Finally it will return. Now, but in case the size is greater than the MTU and D is not set, then it will calculate the maximum size, it will do the fragmentations, it will do fragments, divide into chunks, then header adding, it will add a header to it, and finally send the datagram, and then you will send the datagram. This datagram will have a large number of fragments. Send the fragments. Otherwise, send this datagram, means send the datagram of such a huge size because system can handle them. So we have, so the three issues are there. One will send the datagram, does not matter how big size of datagram it is, and second will be fragment it if the D bit is not set. If D bit is set and the system cannot handle such a big size, then you have to fragment it. You calculate the maximum size, do the fragmentation, do some adder heading exercise, and send the fragments. And finally, at the end, the reassembly module will try to reassemble them. Now we have a reassembly tables are there, which will able to link them various fragments together. But let's try to see what the reassembly module does. The last part, the reassembly will be done not at the intermediate modules, but it will be done only at this one now, only at the destinations now. So how the reassembly? Because you assume that there are many fragments of this IP header, because intermediate machines are not able to handle them properly. Then finally it have n fragments. You have 20 fragments. It might have 1,000 fragments, and then finally it has to be combined them together. So the purpose of the reassembly module is to combine them. What exactly is job of the reassembly module is to find the datagram to which a fragment belongs to. So one datagram might have many fragments. In order the fragments belonging to the same datagram and reassemble all the fragments of a datagram when all have arrived. If all the fragments have arrived within certain stipulated period of time, it has to be identified which are the fragments belong to which of the datagrams and assemble them. Then finally it's sent to the next upper layer module now. If the time has elapsed, not all the fragments have arrived, then finally it will be the fragments will be discarded. So let's try to see the reassembly module. What it does is, finally we have a reassembly module. So what is the input of this reassembly? The input of this reassembly module is the IP datagram from the processing module. It receives the data from the processing module. So input is the IP datagram. Now to the first part, if the offset value, the datagram, the fragment also has offset value or datagram. If the offset value is 0 and M bit is 0, means the M is more bit, means already is 0, they send the datagram to the appropriate queue return. Now basically, let's just start with the, I will just show you the parts of it which you will understand. If what it does, just assume now, if all the fragments have arrived, this is where we start now. The crux of the what it does is, if all fragments have arrived, again the time has not expired. If all the fragments have arrived, reassemble the fragment, and deliver the datagram. Finally, once you have reassembled them, you deliver them to the upper layer protocol. In otherwise, let's say here itself, what I will do is else. For example, what happened that not all have arrived and the time has elapsed. So what we'll do now, here check the timeout. If timeout has expired, if timeout has expired, then discard all the fragment and send the ICMP message. So it does basically primarily two things: checks the timeout. If timeout has not expired and all fragments have arrived, then it will reassemble all the fragments. If fragments have not arrived and timeout also has expired, it will discard all the fragments and send the ICMP message. Again, this sender will send all the packets. They might be following the different routes. They might be having more fragments, or they might not have any fragment if a routing machine or if the routing module is able to send them in one go itself. So these are the important components of this, what we'll call them, we have of this one now, of a IP processing module. One, I will take a small example because another important thing what we do in the IP is what we do. How do we do some checksum? How do we calculate the checksum? Let me just give one a small example to understand how the checksum is basically done to check whether the fragments or the datagram they have received is correct datagram or not. So basically the basic theory behind the checksum, which I will just show you, is the first thing, that the checksum in the IP datagram checks only the header part and not the data part, because the higher layer protocols that encapsulate data in the IP datagram have a checksum field that covers the whole packet. So anyway, the process I will just show you what they do, but the basic theory is, basic processes they follow it, that they take whole IP header into several sections of 16-bit each, add all of them, and initially the checksum field is 0, add all those fields including the checksum value which is 0 of n bits of which value of n is 16. They take sum of it, they take one's complement of it, and then this value is inserted into, encapsulated into the IP header with IP datagram, and this finally the IP datagram is sent to the next router. At a router at the destination machine, at the next machine also similar process is done. They do the sum of all the sections of 16-bit each, including the checksum, and takes after taking the sum, they takes one's complement. If the one's complement is 0, then if one's complement is 0, it means that the datagram arrived at that machine is correct. If not, it means that it has been corrupted. 1 has become 0, 0 might have become 1, and so on. What exactly it is all? Let me just show you with one small example. I have explained you the process. Let me just show you one small example. Now, this is my IP header, this format. This is just, you know that IP header has many fields. It has a version field, it has a checksum field, it has a header length field, it has a total length field, it has service fields, it has a source address field, it has a destination address field, it has an option field, and so on and so forth. So this is what we have. Now this is my IP header format, which has a number of fields. What checksum does, that it aligns, it divides the IP header into 16-bit of sections. So it collects this section. Moment it becomes 16 field, it forms the next section of 16-bit. It keeps on forming the next 16-bit of sections, and finally adds them. Now what I'm trying to do here is, let's say the first field, that is version field, the value of is 4 bits. The second one is 5 bit. The again is 0. You try to check from your books that which field it belongs to, and this is the value of that field. 4, 5, 0. That's a 28. Then we have the next. So here this might be, this is a 4 bit. I remember this is a 4 bit. This is a 4 bit. This is 8 bit. So it becomes one section. Now this 20. This again is 16 bit. This becomes a second section, which you will see now. Then we have the up to here, the next field is a 1, and then here is a 0. This is a 0. Then this is a 4. 4 is 8 bit. I think from here 8 bit. Then we have a 17. The value is another 8 bit, and then we have a, this is a, so 8 bit, and this is a 16 bit, this is a 0. These are the different fields. You compare from your IP this format. Here is simply value, and then this is my source address of 32 bit. This is my destination address of 32 bit size. So this whole becomes 32. This is another 32 bit. This is another 32 bits. This is my source address in 4 octets is written 10 to 12, 14, 5. You try to find out which class it belongs to. Then we have a destination address 12, 6, 7, 9, again 32-bit fields. So again you try to find out which class it belongs to. Already we have discussed this one. So now this is my IP header fields and its equal value. Now I have to find out, and in fact this is my checksum. Initially the checksum field is 0. Now I have to find, before sending the packet to the next, I have to calculate its value. So what I will doing is, I will just show you some basic exercise here. I will be converting them into the binaries and aligning them into different sections, adding all these sections, putting the value of checksum, sending it another side. Again the reverse process will take there itself. So basically it will something like this. I will not show you complete. So 4, 5 and 0, it becomes one section because this is a 4-bit. This is my 4, no, I will not write here. This is my 4 bits. This is another 4 bits. This is 8 bits and this is a 16 bit. So what we have is, so 450 will be written into binary 100. One exercise I will do for the only one section. 0100, this is a 4. 0101, this is a 5. And this is a 0 is of 8 bits. So I will write 0000803. So now what I have done is, this is my one section. In fact, I will just write, this is my one 8-bit and this is another 8-bit. But it holds 16-bit, 8-bit plus 8-bit becomes one section. This will be added with this here. This is my another section. The another section is this one of 16-bit. So I am taking the first row has become two sections for me. 16-bit of 4, 5 and 0. Another section is of 16-bit where the value is 28. Right? So this is my second section. So I am just writing 28. And again 28 I will convert them into 450, okay, right. And then this 28 I will be converting them into again binary. I will be converting them. So it will be binary of 28 will be 16 plus 8 plus 4. So I will just trying to do right like this. 28 will be this is my 16. This is my 8, this is my 4, this is a 0, 0 and all will be 0. Something like this. I mean, you have to align them. So this is second subsection. So this is my section 1, this is my sections 2. Now what goes into this one? The third section is 1. So now section 3 becomes 1. Again I will put them into the binary. Now 1 means this 1 and remaining are 0. So this is way, now my 0 and 0, this will be my section 4. Again equally all will be zeros here, simply zeros. All the 16 zeros. 80 for this one and 80 for this one. Now we have 16 zeros. Now the next will be 4 and 17. Now 4 and 17 will be again, it will be written into 4 and another part will be 17. So this is my another section. Then 4 and 17, this is 0. This 0 will be another subsection because 16-bit. Now 10 to 12, this is 8-bit. This is another 8-bit. So 10 and 12 will be another subsection. Then 14 and 5 will be another subsection. Then we have a 12 and 6 will be another subsection, and 7.7 and 9 will be another subsection. So we have section 1, sections 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have formed the 9 subsections. Now this 9 sections again will be added here. I will get some value. You do this exercise on your own. You simply must know 0, 1, how the 0 and 1 is basically added. This will be added. So sum will be here something. I will get some value in terms of some 1s and 0. In fact, if you do proper calculations, you will be getting something like this. This is what you will be getting after adding them. Now you take the checksum value. Now you calculate the checksum value, CS, checksum value. Now checksum will be the 1, 0, 0, 0, 1, 1. This becomes 0, this becomes 0, this becomes 0, this 0 becomes 1, this becomes 0, 1, 1, 1, this 0, 1, 1, and something like this. So I am taking the ones complement of all these things. Now this value where will be inserted? This value will be inserted here. This value is going to be inserted here, and now this will be sent after inserting the checksum value. It will be inserted by the header adding modules. It will encapsulate this value there. It can encapsulates the data. It encapsulates the checksum value, and then after adding this one, this value, this will be sent to the next router, and another router, the similar exercise will be done. What this will do, the receiving one, it will check whether this packet which they have received is correct packet or not. Similar exercise they do when we send a character, but there the algorithm is simply very simple one. They do parity check or the even parity or the odd parity, but here the exercise is much more difficult. So now what the receiving module will do, the next one for example, again they will add similar exercise they will do, but this time the checksum value will be not 0. Here the checksum value was 0, but that time after you have inserted the checksum value, it will have some value, and it will take some additions of, it take the sum of again all the subsections. We have added 9 subsections here, and then takes one's complement. If you take one's complement there, then finally what we will do is that, and take the add and then take one's complement of add. If at the receiving side the one's complement plus sum of some value, if it equal to 0, then what we have is that everything which we have received is correct, otherwise the packet will be discarded. So this is what we have done with the, let me briefly summarize what we have discussed. We have simply discussed the IP package. IP package is a huge package, is a massive package which comprises of large number of modules, data structures, queues, several data structures. In terms of data structure, it has the input queue, you have output queues, you have a routing table, you have MTU tables, and some other tables it has. And then some of the modules it does is the reassembly modules it does. It has a fragmentations module, you have a forwarding module, we have a header adding modules. For example, it adds the checksum value there. Then you have a processing module, that is the most important modules of all. So these are the important components of this one. Of all, you have to be, some of the basic concept you have to understand about the, this makes the complete discussions of the IP packets and IP. Some of the concept which we have discussed is that the error detections method used by IP, the checksum value, this is one we discussed, and so on. Now some of the questions we try to answer them, so that you must be thorough with the subject as a part of exercise. First thing what you have to do is that you must be able to calculate the checksum. Either it is given into binary or it is given into the hexadecimal format. You must be able to calculate the checksum value. Given the byte sequence of IP datagram, you must be able to calculate, must be able to decide where is what, where is the header length, where is the total length, how many hops it can travel, where is the checksum value, whether the packet is correct or not, in what cases the packet will be rejected, in what cases the packet will be accepted, how the packets are fragmented, how many bits of this you have here, there, how many bits of what is the size of a fragment, and so on. So let's say once we have, once we know all these things, we can try to solve certain problems also. Now, for example, question: which field of the IP header change from router to router? This is the questions we ask now. That's some of the basic fundamental questions. Which field of the IP header? You know that IP has many fields. IP header has many fields. There is a version field, there is a header length fields, and so on. So now which fields of the IP header change from router to router? This time to T, while I was discussing these various algorithms, the field which I have mentioned is called TTL value. This value is decremented by each router. So this is one of the field which keeps on changing from each router to another router now. Now questions can be asked. You calculate the HLN value, header length value, if the total length is 1200 bytes. For example, given the value like this, given the value of, let's say, H, you have to calculate the HLN. This is the most important frequent questions we keep on asking, that given the header length HLN, you have to calculate it, and what is given to you is the total length is 1200 bytes. Total length is given. This total length of your IP datagram is 1200, and the data is data field, data size of data is, let's say what we have is 1176. This is the total length field is total length of bytes is 1200. The total data size value is 1176 bytes. Now what is HLN? You simply calculate this, just deduct this value 1176 from 1200. You will find what is the HLN value. This is very simple. Now another question is the what you can do is question is the value of HLN. The another question is related to HLN, because we ask many questions. Now here in these questions, what we do in the first exercise, what we did is you have to simply find this one given these two values. In this case, what we are trying to do is we have to find option bytes given this value. Let's say exercise 2, what we are trying to do is that you have a IP datagram. Let me see now. Yes, the value of HLN is 7, and you have to find out what is the option bytes, how many option bytes are present. So now what we have to do now is so this is a 7 means, so it means that header length is 7 multiplied by 4, that is 28. Now the minimum of the header length is 20 bytes. So what we'll do now, 28 minus 20 means 8 bytes are left for the option bytes. This is basically what you have to do now. The last questions I will take down is the size of, now this is what is given now. The size of the option field, now option field is given to you, that is 20 bytes. The size of the option field of an IP datagram is 20 bytes. What is the value of HLN? And try to calculate them into the this one now. Now what we have is the 20. It is given means what we have is by default is a 20 bytes now. See, by default is a 20 bytes. The HLN is by default is a 20 bytes, and the value is 5. So basically it is a 20. And by default is a 20 bytes, which you can convert them into the binary and so on. Anyway, let me just quickly summarize once more that what we have discussed. What we have discussed, that is important point related to the IP. That the IP is a connectionless protocols. It is an unreliable protocol, and IP, to provide the reliability, it basically tries to tie up with the TCP protocols. Now in this IP package, we have defined several modules. This header modules, the IP header, header adding modules, fragmentations modules, and some other modules. We define several data structures in terms of the input queue, output queues. Then we have a different tables we define used by different modules. Also we try to do some exercise how to calculate the checksum at the source side and at the receiver side. Thank you very much. लास्ट प्रॉब्लम, कुछ खोज रहे थे, खो गया मेरे पास.